deixa ele ligado. Ok.
Então é o seguinte, aí a gente criou a associação na questão do PJ, ganha uma capacidade de captação de recursos com Thank you, everyone who arrived on time. We're going to start the day because in the afternoon session, we have people connecting from Rio de Janeiro, from Rio Grande do Sul, from Colombia, and from Chile. And so we have this interactive panel, so we should keep the time so that they will join us at the proper timing, as already set. And I'll be chairing this session. So I'm pleased to welcome Luca Pezzati from the National Research Council in Italy, who will give us a welcome and overview of the sessions. Then we'll have that's the part of the overview already.
Shall I be silent on Feijoada or can I announce? Yeah. Good morning. Welcome to this second day of bilateral meeting. Hyperion E-RIHS Anticipa. The program of today is more scientific than yesterday, as I say, closing yesterday's session. A short presentation, average 15 minutes, about scientific activities on both sides which are relevant for planning future cooperation. There's a bit of movement in the morning sessions because Emiliano Innocenti is not here, so I promised you I will present DIGILAB this morning. But first, Marcos will speak about Computer Science Department. Then I will speak about DIGILAB. Then we will have one presentation less in the session number 2, Innovative Instruments and Methods. For those of you interested in that presentation, it will be replicated in the Mexico City meeting next week, which will be streamed. So actually, you could have a chance with 4 hours of lag to assist the Marta Castillejo, because she will, in Mexico, it will be given by the right person. Marta Castillejo will present that. And then we will have a coffee break. It seems to a decent half an hour. So we hope to have a relaxing coffee break. Then we will have good practice and highlights for joint laboratories. And I will present the laboratory of the Opifission. And Ado Yorio Vasconcelos, Physics Department of the University of Minas Gerais, will present, I don't know what, because the title is not here. Then we will have the session Advancing Diagnostic for Intervention in Conservation with 2 presentations, one by Michael and the other by Carla here. Then we will have Education and Training with Michel again and Fernando Marte. We will have a short open discussion. I think we will have feijoada over lunch. And then in the afternoon, we have 2 panels, one interactive panel through Zoom, if I understood correctly, with several people connected from other sides of the continent. And then we will have the final panel, and I invite you to consider what I said yesterday, that I would like this final panel to list an action, a few lines of actions to be performed. Thanks. A few lines of action to be performed in the next months, so that we can advance this cooperation and not make this a diplomatic meeting where we speak, and then we do nothing. So that is the idea. So yeah, we will finish at 4 something. Well, so let's start the day. But to start the day, I would need a chair.
Okay, this session is about data and heritage science. We've invited Professor Bismarck Vaz da Costa, who is the head of the Scientific Computing Laboratory of the Federal University of Minas Gerais. So he'll be speaking about the infrastructure and possibilities and experience we have at UFMG with this sort of solutions, not problems. Cleiton, faz aqui que eu sei que é. prefere falar daí ou daqui?
Okay, good morning all. Thank you so much to Luis to this invitation to present the laboratory oh, sorry, not simulation. Simulation is my lab. For scientific computation of the Minas Gerais University. What I want to do is to present you what we have at this moment. Our near future possibilities, and also what we can do in this effort from your group to help to improve this, let us say, expectation in Brazil. Well, our laboratory is named Laboratório de Computação Científica. The name is Laboratory for Scientific Computation. It was created in 1985. I think it was 1985. And in principle, it was a number crunching machine. But nowadays, it's more, our expectations are really broader than this. We want to help in our research needs in this university and of course, in all other bilateral new possibilities. Well, for the research needs, we have, so the number crunching, if this is the necessity, we have something that we name Senapad. Senapad is a national center for computation. And we have at this moment a Boo machine with 800 processors and with a storage of 10 terabytes, but that we can improve for probably up to 100 or maybe more than this. I am talking about this because I know that one of the most important things for you is the storage. We can go up to 100 here, and probably more. We are in the process of buying something that we can go up to more 1,000 terabytes. It's not much, but it's for a beginning. It's a quite nice starting point. This machine, this Boo machine, it's a 5-year-old machine. We're trying now to move on and buy a new one with around 1,000 processors. It is, we can make parallel processing. And this new one we're trying to buy, we can also use several new research. I will not go into this because there are some technical aspects that it doesn't matter at this moment. But It's probably 10 times faster than this one that we have. But let me see. Oops. I did something stupid here. Yeah, I'm sorry. I'm sorry for this. I don't know the messenger. Okay. So, but this one is essentially what I'm naming the number crunching machine. Of course, this part and this part we can use for other things, not only for number crunching, but mainly the storage. And on the other hand, if you don't, we have another section here that is a software support. What I name not number crunching. I named this one. We have a software support. We can host servers. It means, for example, if another institution like or another department like Louis' department wants to buy a new machine, it doesn't need to make all infrastructure again, but you can host these machines in our lab. We have now a multimedia room. This one is brand new. It's quite nice. We can make fast connections with other institutions here or around in Brazil or everywhere in the world. We have the storage device. Part is here and part is only for non-crunching work. And nowadays, what I'm doing is to make some arrangements with other labs. One is the microscopy, and Carla is here. We're trying to make something to help them to store images. What they do there is just en passant is to take pictures of proteins or this kind of cells, of this kind of things, and they have to have high quality pictures. Let us say one picture is something like 100 megabytes, and what we can do is to have a storage for those pictures and so on. I think we have the same kind of problems of storing pictures. And geoprocessing, this is a guy from geoscience. In this lab, what they do is to make projects for example, railroads, for example, that they project a railroad from Amazon to South Brazil, and they have to pass from special places, not in this town, but in this town, we have to evitate this river and this kind of thing. This is a quite complicated thing to do, and it demands a lot of number crunching and also a lot of storage. Then we are in the beginning of doing an agreement with these people, and this is very nice, this LCC human. It doesn't mean that this LCC is not human. It's also human, but this one is just this LCC human means the laboratory for computation, but having the human science, the soft science. That's the idea. This one was created in the 80s it was a demand from the physics department, chemistry department, and so on. But now this one is a demand from history and people in political science and so on, and also people from the Luis department, they also enter in this kind of new project. So this is the near future. This one we already have, and here also, as I told you, we have also and near future demands here that I believe in 2 or 3 years we will be able to go in this stuff. And just to finish, our human resource in our laboratory, we have, of course, administrative staff because they have to take care of our payments and so on. Those are important guys, and then we have a technical support for assessing the cluster. This guy is capable, for example, of helping you how to assess the best way to assess the cluster and so on. We can install the software you want in the cluster. If you have new software, you develop a new software, or if you want to develop a new software, we can help you in these kind of things. And this one is brand new. Install local multimedia rooms. We have now the technology to install this multimedia room that I told you before in the first slide. We can help to install this multimedia everywhere you want with the same technology that we had there. Is something which is cheap and easy. And we have also a section where we develop some administrative resource. I mean, how to assess the cluster without bureaucracy. It means we don't have to fill papers and forms everywhere. We do this once and that's all. This simplifies our life doing this. I know that many people just give up of assessing the cluster just because the bureaucracy was so huge a few years ago, but now everything is quite simplified. Well, that's what in a few lines, what I can tell you about the laboratory. And I would say that we can and we will do everything to help in this new ideas and so on. Anything that is in our it is around. And thank you again for this kind invitation.
Obrigado. So thank you, Bismarck. Well, we visited the scientific computing facilities the day before yesterday with Luca, and they've been very active throughout the history of the university. So it's very welcome this positive sign, and for sure we will look for your yes. Thank you very much, and for sure we will be looking for your help. So let's move on with Luca, who will be speaking about the DIGILAB.
Thank you. Thank you, Luis. So, this very famous platform. You saw yesterday several beautiful examples of what the physical access platforms of E-RIHS, Hyperion, can offer to heritage science. You were able to see good examples because those platforms are operated since more than 10 years by specific European projects. Concerning DIGILAB, is kind of speaking of Neverland, because DIGILAB is the platform which is not there. It's a plan which started with the idea of E-RIHS, so started 3 years ago, and after 3 years, it's still a plan. It's the best known plan in heritage science around the world. Only this year I presented it in Taiwan, in San Francisco here, and next week I will present in Mexico. Why this? Because even if it's a plan, we will implement it, and this will be the platform probably of the infrastructure enabling the international cooperation for real. What we want to do with this digital platform for E-RIHS? First, the problem is that all the rest of the infrastructure is practically producing data, producing digital data. The measuring platform, FixLab and MoLab, are producing measurement data. ArcLab is producing scientific data with the analysis of what is in archives. And probably in the future, several parts of ArcLab will be digitized. You know, we have ArcLab to allow researchers to go to physical archives, but in the future, maybe the physical part of these archives could be digitized, which is not in this moment in Europe. You consider that more than 90% of what is in museums archives, I think, 80 to 90% is still in physical form, not digitized. Of course, this will change and change rapidly, but for the moment we need ArcLab. Also, you remember ArcLab is to access samples, and that would be difficult to completely digitize the information content of samples. So there will always be an ArcLab, but also there will be a DIGILAB. DIGILAB is answering one of the core missions presented yesterday: establish a common infrastructure of open data and services. DIGILAB is also the platform probably having more users because it will not require physical access. So costs of accessing the platform will be almost zero. We started with this idea that E-RIHS is a data producer. Initially, we thought to collaborate with existing European infrastructure, digital European infrastructures, for solving the problem: who is going to save the digital data produced by E-RIHS? And we started trying to set up a cooperation with the most, let's say, what seemed to be the most promising partner, which is DARIA, the digital research infrastructure for arts and humanities in Europe, which exists. And we started discussing with DARIA, but then we realized that DARIA was born with the concept of publications in mind, not scientific data set. So it's more an infrastructure which is handling text, videos, these kind of things, images, but is not an infrastructure capable of managing tomographic cubes, three-dimensional models, and so on. So after a few years of discussion, we ended up with the conviction and conclusion that we need to create our own platform to handle this kind of data. That is scientific data sets, not publications. Publication can be handled by lots of infrastructure today in Europe. There's OpenAIRE, there's a lot of repositories for open science and publications. So there's not a place to find data sets. And if you think there are not so many data sets about heritage around, also for lots of reasons, IPR, I don't know where to put them, I don't know if they're useful, blah, blah, blah. So what we have in mind is to create one. How will we try to set up this platform? First, you need to consider which is the air in Europe about data. The air was totally changed with the concept of open science, open data. I think it's changing all over the world, but this in Europe is particularly strong because of a very simple reason. If you don't open your data, the Commission is not giving you money. So you see, we have very good reason for the culture of open data, open science. If we want to get grants, we need to open data. Oh, the principle is simple. What is paid with public money needs to be public domain, let's say, owned by the public, and so open data. So as I told you, there is a landscape. So we are working with other infrastructures. We still cooperate with DARIA. DARIA is one of the partners in the E-RIHS preparatory phase. We are cooperating with this cluster project, which is called Parthenos. Ariadne, the digital archaeology community, just entered the second integrating activity, which is called Ariadne Plus. So they will continue providing a service for integrating archaeological digital data sets. And then there is a new cluster, Social Science and Humanities, Open Science Cluster, with this very strange name, SHOCK. And this cluster will start in January next year. And within this cluster, we will do more research oriented to launch DIGILAB as it should be. I think you know which are the most problematic issues if you want to share data. The first thing I say that, look, we need to go to a policy of opening data. Most people from the museums in the hall, they look at me like I was totally crazy, gone mad. And then I explained that, no, it's impossible that you keep your data locked, because at least if you want our analysis, you need to open the results. Yesterday, Bruno answered about the question, who is owning, where we are putting now the data? Situation is quite strange, because the rules started many years ago where no open data was around. And explicitly the rules saying that the data is owned by the users, which is the rule in integrating activity. Actually, it is no more consistent with the idea that the data is publicly owned. So we are in this mid-range, which is very strange, with the rules, the old rule saying the data set is with the user who called for the project to the infrastructure. And the other rule that the data produced by the infrastructure need to be open. So we are just in between in this moment. Actually, we are safe. We don't yet have DIGILAB, so we cannot publish the data. But we will, and so the user, they have time for embargo, let's say. So what is known by the Commission, luckily the Commission already knows that, especially in our field, the situation of open data is this. The data is open by definition, but actually it is restricted by necessity. Another point, IPR management. You know, each single piece of heritage, they have the owner. This could be private, could be public, could be a museum, could be a majority, could be a local community, could be church, you imagine. So handling the ownership of the data is a nightmare, and it needs a lot of work. So there is a solution for this, and this is the Ariadne approach. The Ariadne approach is, for the moment, we create a registry. We don't have the data. We simply tell the researcher, look, the data exists and it is there. Then if you want to access and there's problem of IPR, you negotiate directly with the data owner. Either for doing this very simple thing, there is a lot of troubles, because for pointing to a data, you need to have metadata. So you need to describe it. Is there any standard method in the world or just in Europe to describe heritage science data? No, it isn't. There is no such a method. So this is the first problem. We need to create a consistent system of metadating, describing not just the object, because I think describing the object in the sense as a piece of heritage is not our business. It's the business of Ministry of Culture, which they keep catalogs of heritage. So strictly speaking, it's not the business of E-RIHS to describe digitally the digital description of the piece of heritage. Of course, we need it, but it's not our business. So we hope that somebody will do that elsewhere, so that we simply can link. The moment that we measure something, we create a data set and we point in the digital world to the description of the object. We don't need to describe the object again, otherwise the situation for a single measurement will take weeks. So that is what we hope, that in some time digital representation of heritage will have their place. They will be, let's say, digital objects in the new internet, because you know, we are going towards a new internet. They will be digital objects. They will have their persistent identifier to which you can point, and so each measure made by the infrastructure will simply link to something existing, describing what we measured. So we remain to create a metadata system describing how we measured and why, maybe. So that is, and this researcher will be able to browse our registry and to decide where to access the data, for instance. But the situation is working also in the other direction. If the link is working, accessing the digital object of the artwork could enable you to access all the measurement and tests performed on the artwork. So it's very clear where we want to land in the future. It is much less clear how we can land to this wonderful situation into which you simply open the digital image of an object and you know all the history of restoration and measurements made on it from all the parts of the world. And that you easily understand that this is a global problem, because no single continent can handle such a complexity of information, especially when it comes to artworks. So we will create a registry of data, but that is not enough, because once you have the data, you need to probably use it. And so to use the data set, we will need to create also, I don't say tools, of course, in the future we will create tools. We will probably store our own data, the data directly from measurements. But for the moment, we can simply try to tell the researchers, look, there are very good tools around for you to use the data sets. And so DIGILAB will be a registry of data and a registry of tools, softwares, where you can find. Also here, there is a lot of trouble, a lot of discussion. One of the probably easier things will be to find an image viewer, a format for exchanging images. There's a lot of discussion about that, and a lot of people are using IIIF, for instance. I didn't even know what that was, but now I realize that there are few viewers around which are going used by a lot of people, like Mirador. There is another example for 3D, which is produced in Italy. A lot of people use 3D Hop, use the MeshLab. MeshLab is a project to which I contributed when I was very, very young, because the colleague in Pisa, in 1999, we met, and they started developing MeshLab over datasets, real datasets that we produced at the institute, so the cooperation dates back a lot of time. Oops, sorry. I will fight with this pointer with all my life, but I saw a lot of speakers fighting, because the position of these two buttons is unnatural. You should use this way, but you fire the laser at yourself in that case. Well, what is the point? So you understand that we are aiming at creating a virtual research environment, practically speaking, a place where you can enter, you find the data, you find the tools, and you maybe use the software. So where are the data? The data are in repositories all over the world. I don't care. DIGILAB is not a physical infrastructure. Where are the tools? Most probably, if Europe will be good in creating the European Open Science Cloud, probably most of the tools will be cloud-based. I don't say the data will be cloud-based, because too many data, and the European cloud has not these storage capabilities. So I think that apart from providing researchers a set of good and common services, I don't think the cloud will become a cloud for storing datasets. They are already stored in repositories. So the big data producer, they have already their own repositories. So we point to have a virtual research environment cloud-based. As I explained you, this very tough point for the moment will be solved with, okay, it's up to you, researcher, to establish the condition for using the data with the data owner. In the future, that will be not. When we will start producing data with the infrastructure, we plan to have the data not in DIGILAB. DIGILAB is not a repository, but we plan to have the data accessible by DIGILAB without this last mile problem, because we will contract directly with the users of the infrastructure, and we will, in the contract, we will establish the terms, and after a certain period, we will release automatically the data we collected in the infrastructure measurement. That is what we are thinking to do. This is just the scheme of what I said, is not adding information. We planned to open in 2019, but now I'm realizing that that may be an optimistic approach. And of course, as the infrastructure will open as an ERIC in 2021, probably there's no need to hurry. Well, the major point and the final point of DIGILAB. DIGILAB is the part of the infrastructure which can be easily shared with all the world, with a real cooperation. Because there's no need to move people, so there's no need to buy plane ticket. And so there's the possibility of real use of data across different places in the world, which is the base condition for this to happen. The base condition for this to happen are two. First condition, we in Europe, with E-RIHS, we are able to create this open data system so we can share European data in heritage with the rest of the world. Condition for a cooperation on the other side is the other side do the same, be in the US or Mexico or Brazil or China. They open heritage data, and we can create the cooperation on the basis of having data providers in both regions, and that data provision can be actually, so this platform could be one and the same, with different providers actively being partner of the, not of E-RIHS, of the global infrastructure that we will think launching when E-RIHS will be operative. So, rules are to be set. In Europe, DIGILAB will work just as the other platform based on the in-kind concept. So services provided to the platform will be provided in kind by the facilities in Europe. I don't see any particular problems that this is the same approach outside Europe, because if we have, let's say, a bilateral agreement between E-RIHS and another infrastructure in another place in the world, we could set base rules, but the rules of in-kind could apply as well. So you will have your institution providing services to the platform. And then, of course, the benefit of taking part to the same platform, you know, in the digital world, everything is about permissions. So people inside DIGILAB will have top-level permission for exchanging data, software, and blah, blah, blah. People outside will have less favorable conditions, and this is what will create this worldwide digital infrastructure. So frankly, we are waiting to see the first implementation plan, because you understand that this is very, very difficult. We have a few years to create a good model. In the informatic world, in the digital world, if you don't create a good thing right from the start, you will lose your potential users, because they go to your web portal, they say, oh, what is this? It's horrible. And they forget about using it in the future. So we need to open something which will not be horrible, will be right good from the start. And that is why it's better not to hurry. So, And this ends the presentation of the mythical DIGILAB platform that I hope will be one of the best successes of E-RIHS in the future. Thank you. Obrigado.
Thanks, Luca. Thank you, Luca. So the last presentation of this session is innovative instruments and methods for integrated approaches to cultural heritage analysis and diagnostics. And there are two speakers, Professora Dalva Lúcia Faria from the University of São Paulo and Professora Ana Maria de Paula from the physics department at the Federal University of Minas Gerais. Dalva, please. Since you will be, já que você vai ver, você pode ficar aí, a hora que for a sua apresentação eu te chamo, tá bem? Pode vir, se está aberto aí.
Again, good morning. I'd like to thank the organizing committee for the invitation. My apologies for my voice. The celebration yesterday was... Well, and I was double-minded about what to talk to you this morning, because it's such a huge possibility of discussions, and there are so many topics. And considering the very short time, I decided to make kind of summary of what we have been discussing before this week. And of course, with my own interpretation of in some aspects. And this is what I put in here. So many areas, and it's literally impossible to talk about innovative instrumentation and methods on such a huge number of issues. So what I decided to do was to start commenting that the situation some decades ago was having this hard science, hard scientists, and soft scientists and conservators, restorators, and other people directly linked to cultural heritage investigations. When they work together, they used to work together in their own spaces. And there was no this interface. So the communication was much more difficult. And I'm talking about the last 3 decades, more or less. But the situation we have today, fortunately, is a little bit different. So we have now the conservation scientists, and discussions are much more focused on the cultural heritage problems. But I'd like to call your attention that even so, we are not, and this is the good point, I mean, we're still keeping the experts in their own areas. So, of course, as Antonio, Fernando, and other people here mentioned, we still need the experts, because sometimes the issues to be addressed are so specific that we really need experts in that field. And I'll give you, I'll put it in context in the next slides. One thing that I really like to emphasize is that this integrated approach must include, when we talk about integrated approach, we always think about multi-analytical approach to investigate an object. But again, the staff has to be this specific expertise. Every time I have the opportunity to talk, I mention this. Particularly in my expertise area, I'm a vibrational spectroscopist. And of course, Raman spectroscopy became a very popular technique in the cultural heritage field. And it's very common. Nowadays, you can buy push-and-play equipments. But what I notice is that people generally don't have enough information, first of all, to acquire properly the data, and second of all, to interpret it properly. And this is, when I'm reviewing papers, for example, and people who are not experts use Raman microscopy, Raman spectroscopy in general, there are so many errors in interpretation in the way the experiment is conducting. And this is very worrying from my point of view. So this integrated approach, again, it's very important to have experts considering the complexity of the problems. Of course, it's not always you have complex problems. Antonio, Fernando mentioned that before. Sometimes you can work out a problem just by eye or by using very simple instrumentation or a very simple approach. So again, the issue is what kind of problem you want to address. What's the question? I always make this clear to people who come to me. And I always say, okay, when I put your sample in my microscope, in the microscope stage, and I had a look of it, it's a kind of, it's a universe of spots or aspects I can explore. So please restrict exactly what your problem is. Isn't it, Fernando? So, this complexity, again, not necessarily means that we need highly specialized or highly innovative techniques. It is very important to emphasize that normally cultural heritage investigators or investigations in the cultural heritage field frequently use well-established techniques, which are used by in other research fields, by other experts, by other academics. And we benefit from instruments developed with a specific purpose. So, for example, perhaps the best example I can imagine now is the instrument miniaturization for the exploration of the Mars surface. For example, there is a Moosbauer instrument, which is about 2 kilograms in weight, which was developed for Mars exploration. And we are now using it in, for example, rock art paintings for in situ analysis. Raman microscopy, again, the portables, and most of the portables and handheld systems benefited from this kind of developments. So I'm trying to give very general examples of innovation in the field. So now, it was 20 years ago, it was not, imaginable to have this kind of very small, very portable equipments for in situ analysis. Again, as I mentioned before, not always you need highly sophisticated equipment. Again, depends on the questions you have. Antonio pointed out a very interesting thing, that people, there's a kind of, still, unfortunately, a kind of glamourization on what science can do for you. Unfortunately, when I get a spectrum, for example, unfortunately, the bands, they don't come with labels. I have myself to interpret it. So the limitation, several times, is not the technique. Sometimes is the user who is limiting the potentiality. I'll give you, I just have 2 or 3 slides more, but a good example, for instance, this is the setup for nano-FTIR spectroscopy. And this setup is available at the National Laboratory of Synchrotron Light, Campinas. And when I use this facility, I don't use it in my current research. When I use it, it was because I was interested in the very first steps of metal corrosion. This was an investigation where which started with a cultural heritage problem, which Luis Antonio brought to me several years ago on the corrosion of a very small lead sculpture. And then we started an academic investigation and led to this very, very specific and sophisticated technique. This is Raul Freitas, who is responsible for this line there. Again, I'd like to call your attention that facilities are available here and are available outside Brazil. Again, it all depends on your need, on the specific needs of your research. And I'd like to, again, as Luis said, I'd like to call your attention to the potentialities available at the CIRRUS. This is a new accelerator in Campinas. It's one of the top in the world, and they are really very eager to have applied problems to help with. The other thing I'd like to mention is, concerning, I forgot to mention something. Again, because the thing is what innovative means. For me, for example, TERS is innovative because it's one of the frontiers of Raman microscopy. Because of the huge lateral resolution, it's about 20 nanometers, is really very, very spatially accurate. But for example, for a laboratory, a smaller laboratory or perhaps a laboratory in a museum, having a portable Raman system is very innovative. So again, this is very relative. For example, I just mentioned the nano-FTIR possibility. For some museums, having an FTIR equipment, a routine one, FTIR spectrometers are a routine equipment in any chemical laboratory, organic, inorganic, physical, chemist, analytical, any. But in some museums, having one, a very basic one, is really very innovative. And sometimes, to clarify some points, for example, analyzing polymers or eventually pigments, right? Raman, FTIR is a very simple and very efficient technique. But again, this is the sort of technique, I don't have time to enter in detail. This is just to cite that you can get Raman spectra, Raman data, with such a huge spatial resolution. Of course, this is not for any problem. This is only desirable or only necessary when you have very specific problems. Again, I think, as I said before, the limiting aspect, the limiting factor for innovation in any field of knowledge is the human being, is the human resource. And any effort in this perspective must involve the formation of people to use properly this very nice information that some state-of-art techniques can provide us. So thank you very much for your attention.
Thank you, Dalva. So I'm pleased to invite Professor Ana Maria de Paula. Desculpe, Ana. Tá bem. USB. Tem algum aviso? Alguma coisa? Talvez... Não, então, pois é, então, mas para mandar para qual página? Porque eu posso anunciar aqui. This afternoon we have the interactive panel, which will be transmitted over the regular page of the UFMG CAC. So for those who are attending the event through the internet, that's the same address, the very same address, which changes if it's the morning session or the afternoon session, but it's all housed within the YouTube page of the CAC UFMG, CAC UFMG. But for the afternoon session, which is the interactive panel, we'll start at 1:30 sharp, so I'd like to ask you all to be here at 1:25 so that we have time to be all set and start the session on time, because there will be colleagues from Rio de Janeiro, from the undergraduate course in Conservation Restoration at the Federal University of Rio. The course coordinator, who is also a scientist, Professor Daniel Andrade, will be with us. Professor Daniele Fonseca, from the Federal University of Rio Grande do Sul, from the Federal University of Pelotas in Rio Grande do Sul. Professor Daniele is the course coordinator for the undergraduate course in Conservation Restoration of Cultural Properties at the Federal University of Pelotas. Two colleagues from the Centro Nacional de Conservación y Restauración in Chile, National Center for Conservation and Restoration in Chile, Maria Espinosa and Tomás, a biologist and a chemist. They will also be with us over the Zoom platform. And from Colombia, from the Universidad de los Andes, Mario Omar Higuera will also be with us. So we'll have a panel which will be open to everyone. Those invited panelists will have a short time to speak about their experience, the course they're running in their universities, in the case of here in Brazil, Also for those from Colombia, Mario Mar, and he'll be speaking about the course in Colombia and the research activities over there, and the same for Chile. And then we have our panelists here at the meeting facilities, and it's going to be an open session for discussion after we have this short presentations. So the aim is to open more, and it's a very first experience for us. We've tried it already here in the morning. We did a dry run. It worked well. So hopefully everything will be all right for the afternoon session. And I'll keep talking until they finish here, but... Tá tudo bem? Deixa ele... Ok. Tá tranquilo. Tá bem. No intervalo a gente... vídeo de quantos minutos? Tá bom.
Okay, good morning. Sorry for the computer problem here. And first of all, thank you very much, Luis and Willie, for inviting me here. It's my first time to talk to a different audience of arts. And so I'm going to be talking today about this technique, which is hyperspectral imaging, which has quite a broad application. And one possibility is, as was just said before, it's a technique, and how to use it will depend very much what the problem is that you want to solve. But there are some interesting ways to apply it to artworks. And so my name is Ana Maria. I'm from the physics department here in the UFMG. And Barbara is my PhD student who's working in this technique. Gladstone and Gabriela also are students in our group. And the people in Italy, the group in Italy, where Christian Manzoni was the sandwich supervisor of Barbara, where we started to work with this technique together. So I'm going to start to talk to you today what is hyperspectral imaging. Well, photography and images is quite well known, and the first ones are just the black and white, very old cameras. So we start with black and white, then the photography moved to be able to have color sensors, and so we had the RGB possibility of getting colors into an image. And then we can do also spectroscopy, just try to see all the range of reflectance in terms of wavelength in a point, in a figure. But the ideal one is just to try to merge these two and get a completely information about the spectral resolution in an image. And so one which is quite well known already is multispectral, which is just get some photos with different filters. So you can get a composite of what are the colors part of an image. But the ideal one is just to have the full range of spectral information at each point in the image. And so that's what is being called hyperspectral image. And so in this way, what we have is that you have an image with the, say, x, y dimensions, and a third dimension, which is the wavelength information. And so for each point of this image, we can have the full spectral information. For instance, here is being shown the reflectance of a picture. Instead of just the composition of the three colors RGB, we have the information continuous on all wavelengths. And so how to get these images? To get these images, well, the first ones are just the idea. You have a sample that you want to image, and you scan it in X and Y, get a dispersive element, like a prism, and record a spectrum for this position. and then run it for all the positions and get a cube of information. But that's very slow and very time-consuming. It is being developed to get, instead of just a point, get a matrix detector, so you can get a line of that image in a go. Or for the multiple spectral ones, you can get filters at its specific color and get some positions in this cube. But for the hyperspectral, you need to get much more sophisticated way of recording the whole spectrum in a point. So there are some commercial equipments where they do that with quite complicated moving parts and having dispersive element, which is also very difficult to do and very time-consuming. And so the idea here is just try to get the Fourier transform spectroscopy and be able to get a small Fourier transform spectrometer to be able to do it in a portable way. Ben, Fourier transform was being already mentioned here. What you do, you divide your wave in two parts, get a moving one where you put your sample, and then when you recombine the two together, you can get an interference pattern that depends on the wavelength of the sample and its position. When you do a Fourier transform, then you get the spectrum of a point. And so what we want to do is just try to get that in a way that you can do it with a full image. And so the idea is to use this phenomenon, which is birefringence. And so it's a crystal with two different refractive index, depend on the axis of the crystal. And so if you look an object through this crystal, you can see that the light is divided in two paths. And so the idea is just to use birefringence to get that interference pattern. And so this is a patent from the people in Italy, from the Milan group, where they use this birefringence filter to build a very small interferometer. And so the idea is if you have a wave with polarization at 45 degrees, and you pass it through one of these birefringent filter, the components in each axis of the crystal will be moving with different velocity because they have different refractive index, and so they have different paths. And so you can get, they separated in time. If you get another piece of this refractive index crystal, but with the optical axis rotated perpendicular to this one, and you get it shaped in a kind of just two wedges that you can slide one against the other, so you can control the width of material that you're passing through the light. You can control the distance between these two pulses. And so by moving these, you move these pulses around, and putting a polarizer to recombine them at 45 degrees again, you can get that interference interferogram. And from that, from the Fourier transform, then you can get the spectral information as well. And that is just a small crystal that you can build in a way in a very small device. And so what they proposed was this hyperspectral camera. It's just a normal camera, and you can use even in just a monochrome, just a very simple black and white sensor, because you are getting the information with the interferometer pattern here, which is just one polarizer. You've got your object here that you're going to be imaging in the camera. You pass it through this interferometer, which is one polarizer. That wedge that moves here to be able to control the overall thickness of this birefringent device. And so you can get with the other polarizer, you can get the interference pattern of the whole image. And so you're just moving this part here, you control this overall distance, and you control then the path of that interferometer. And with that, then one use is just to image a paint. And this work was done by Barbara in Milan. This is just a painting, not well-known painter, but it's a 90 by 9 by 130 millimeter. And here is the black and white image that contains that information in the Z direction. And then by Fourier transform, we can get the actual color. Here is just one recovered image from this painting showing all the details. And we can get from there the reflectance and all the details of the color information in that painting. Just another example is this Egyptian cartonnage, where here is just the recovered color image with just marked here in this point is the spectrum, the reflectance spectrum from that position, the reflectance spectrum from this bluish area, and then the reflectance spectrum from this more kind of orange area. And with this one, also, it was already known, but just to demonstrate, exciting the whole area with a laser at 617 nanometer, you can excite the fluorescence of this pigment, which is part of the blue, which is characterized, which is the famous Egyptian blue. And so you can get, that is just a map of the fluorescence intensity of this whole area. It's false colored here in green just because it's the range of emission of this pigment. Then what you can do as well with this technique is it doesn't need to be macro. You can use it in a microscopic way as well. And so that's what we've been developing here in our department. We have changed the configuration, and instead of using the interferometer in front of a camera, we built a microscope with it. We have the objective, the sample, the tube lens, and the camera with the objective. And then you can get microscopic images as well. Here I'm showing just a demonstration how to calibrate the frequency of the system as well. It's just a screen of one smartphone, one Samsung phone, showing the white screen in a telephone is made of green, blue, and red emitters. And we could just make then a microscopic position. And when we get the hyperspectral position on the red, we get the spectrum of the red, the spectrum of the green, and the spectrum of the blue. And with that, we can also study fluorescence of small samples. Just to demonstrate here, we get a piece of paper, where we just, at the edge of the paper, we had it, we show the fibers of the paper here. In this part, there is, we put, just to test, an ink, which is rhodamine, that fluoresces in more to the orange and yellowish part of the spectrum. And at this part is just the white paper that has a bluish fluorescence. And so we are just showing here that we can separate in details also the fluorescence in a microscopic way. So the idea here was just to show you a little bit of the possible applications, and then, as was just mentioned before, how to use it will depend on the specific program that is needed. And then it's a kind of tool that can be used in many different ways, from the microscopic to the macroscopic point of view. So thank you very much for your attention.
So thank you all. Thank you, Ana Maria. So may I call all of our speakers so that we have a short discussion. Bismarck? Nova, yes? Well, this session was divided in two parts. The first one about the data and heritage science. Bismarck, please. And the second one on innovative instrumentation. For the data, I mean, it's very, very important that we start speaking about this because it's really a very complicated issue, and how to deal with the raw data, how to share, how to protect, and so on. So it's really a huge task for the future. And we're glad to know that we can have the support of our university, but this is really something that we will have to deal within Anticipa as well and within our group of laboratories, how to share and how to go ahead with that. And in terms of instrumentation, we are already using several portable instrumentation, fixed units, and it's something also that we will discuss further within Anticipa, because we have to already, for these next 2 years, to set up the fixed labs, the mobile labs, and the facilities as according to the model that was adopted by our colleagues in Europe. But we can see clearly that even here in Brazil, really we are very proud of that. We have already spoken about this, that the infrastructure we have here already, not just in terms of instrumentation, but in terms of qualified scientists and technicians, is already a very good point to go ahead. It's not even, I'm not even speaking about starting. It's just going ahead with the, the potential and already what we have in here. So I'm opening I'm opening the word to the floor, and because of the time and because of the afternoon session, we have the floor for 2 questions or comments. Fernando Marte, Universidad San Martín in Buenos Aires, Argentina.
First, I would like to congratulate all the presentation. They were amazing. And I have just a short question regarding something Dalva said, very important, that now we have access to push and place instruments, okay? So, and she pointed very well that sometimes those data that are acquired for people who are not expert on the field, okay, can be interpreted in the wrong way. Now, my question is to the DIGILAB. So I remember when I was working with natural history collection, one of the most important issues they were facing, it was something that they call the quality of the data. I don't like the word quality, but have you thought about this? I mean, trying to filter or trying to uniform the way they were going to acquire the data, process the data in order to then share it?
Oh, Fernando, thank you for your question. It's multifaceted. First, the problem of opening data to misinterpretation. That is, if you open the data, you open the data to misinterpretation, full stop. It's like you go, you buy your gun, and then you can kill yourself if you want. So there's a fact. How to limit these? Well, is the second part of the question. One of the points of the infrastructure, of all the platforms in the infrastructure, is quality. Quality of the services, quality of the capacities of the groups, quality of the science, which is enabled by the infrastructure. So quality applies as well to DIGILAB, and one of the problem handling is the quality of data sets. So in a certain sense, one of the mission of the platform is to ensure that what is listed and what is registered, pointed to by the DIGILAB, it is a good data. This is almost impossible. In Ariadne, the solution has been to have a point to data warning. These data are not, we point to them, but they are not verified. Otherwise, you can have the quality inserted into the registry. So you point, it's like TripAdvisor. There is hotel with 5 stars, hotel with 3, 4. So it's the same. It's as long as DIGILAB in the first existence of it is an aggregator, we cannot renounce to declare, oh, look, there are some data sets not very well known, we don't know. it's a risk, but we know it is there. So if you want to access, in a certain sense, it's a disclaimer on quality, which is better than hiding that data forever, considering the number of datasets around is not very high in this moment.
I have another question related to DIGILAB, that and about terminology, because in the museum field we have a problem with even describing an object. And for instance, in a photography, you can have the same photography described in 6 different ways. So we are in Brazil actually describing how can we share our collections and have a common terminology. So in the conservation field, we don't have yet a terminology that is full, that all institutions share and all professionals share. So, and I'm with this because if Ariadne works pointing, you at least have to have a kind of equivalent how terms shared can. Though I guess this is how have you been talking about this and another question, but it's related, is that as Alva told, that we sometimes we don't even have to interpret. You have to know many technical how this was exactly done. So how can we describe? Maybe SAIC has a book for conservation that is a guide to digital photography. So as a conservator, I know that how a digital camera works and how to do a good photography with reflection light and so on. And they maybe we must think about a protocol. So a scientist or a conservator will know, I know this is the format of the data expected to have, this is terminology that is suggested to I describe, or so this is the question.
Oh, thanks for the question. I start from the end. Of course, I was saying in many occasions that the real problem of creating metadata is not, because in a discussion of a few days, I think we can converge on something, is not to find a description of what I did. So the measurement, the digital photography, the FTIR, that is something that we could solve. The problem is that first I have to decide which protocol I use for the digital photography, for the XRF measurement, because that is the problem that is before describing the data. Because if I create non-consistent data sets, because I'm using different methodological approaches. So the big problem before metadating, which is a discussion kind of, okay, let's agree on the form for describing a certain measurement. Before the description, the problem really is let's agree on the way we perform a certain measurement, including digital photography. This is preliminary to have the real sharing of data, because if I'm sending you data, but they're acquired according to my rules, for you, probably that data will be useless, and vice versa. So this is the point about having first discussed common protocols. And I think here is a very good chance of discussing common protocols without formalizing them, because we are not an ISO group, we are a research infrastructure with so many components that need to agree on something in order for the infrastructure to function. And so we will practically create our own best practices. And as we are so many countries involved, probably these best practices will easily find a way to become, let's say, standards in the field. For the other point, thank you. This is the elephant in the room. 25 countries, 40 languages. All these people are supposed to search the databases in English. I think not feasible. Well, maybe in future, but why English? So the point is really about ontologies. And we had, Bruno, you remember, an attempt to create a dictionary, Cameo, but that was in English during the first years of the infrastructure. At least to agree on base terms. Yes, a description of base terms in heritage. But I think that we need to have ontologies and translation. Actually, in Europe, there is a research infrastructure for doing that. It is called CLARIN, Common Language, blah, blah. CLARIN is part of the group of research infrastructure in social science and humanities. You see, there's more work ahead than what has been behind. Yes, that is a problem. For the beginning, we will start, of course, with English, and probably we will provide dictionaries, what we mean by those terms. But we know that the solution is short-sighted, because we need at least to have all the major languages spoken in our field. I don't say we'll have a database in Hungarian, but sorry for Hungarian people.
So we are, thank you very much for the contributions. We are running late. I just want to make a last comment that in the case of the work described here by our colleague, Professor Ana Maria, we are very pleased to have her in the presentation, because it's less than 1 week that we know about her work, and we are so close and at the same time so far. So it's a, preparation of events like this, it's really a very good opportunity. So that, thank you very much. Thank you, Dalva. Thank you, Bismarck, for the future works we'll be doing together. And thanks, Luca, for exposing the questions. So we'll go for a coffee break. It's going to be a short coffee break. We have other contributors to the session, and I'll be calling you soon. Thank you.
Pensei o contrário, eu pensei em fazer esse tipo de imagem no meu microfone.
Deixa o lado carregar a apresentação dele, e aí se o vídeo funciona. Ah, tá. Nós vamos juntar. Não vamos distribuir, não. Vamos ficar o nosso. Não, mas o microfone vão acessar tudo junto.
Obrigada. Não, é só porque, na verdade, eu montei aquela figura ali, eu estava em cima dela, colocando os padrões de interferência para mostrar como é que funcionava. Então, aí. Tá, joia.
aí? Já está tudo instalado?
É,
Vai precisar de cortar a apresentação.
não, então aqui, ó, Luiz. A questão agora do.
Não, está tudo certo. Pode manter mesmo, parar, cozinhar, vai. Está tudo certo, ele já eliminou as imagens que não podiam, está tudo ok. So, I'm saying it's all set. Yeah. Então, tudo como está, sem mudança.
Tell them that I'm sorry. Tell them that I will just keep some slides a bit better than.
Good.
I'm sorry for making problems.
Good morning, everyone. Cleiton, pede os estudantes lá para chamar o pessoal. We will move on the next session of this morning. The title of this first, we had the session of this morning is divided in three subsessions. So the first one is good practices and highlights for joint laboratories. One example is the National Research Council Laboratory and Opificio delle Pietre Dure Restoration and Conservation Institute, which will be presented by Luca Pezzati. Thank you for cutting your coffee break. And then we have a contribution of Professor Adojório Vasconcelos, who is also from the physics department, and he is a very respected and well-known scientist who will be speaking about, I asked him to talk about good practices and highlights for joint laboratories. So he'll be speaking to us about his experience in this field. So please, Luca.
Hi again. I almost forgot about this because Raffaella Fontana should have presented. So Raffaella gave me the slides, 84 to be precise. I told her it's just 15 minutes. How can I manage with 85 slides? So I had to reduce a bit. Actually, we are both most involved in the laboratory because I opened it in 1998 and she's running the group and the laboratory since several years. As I'm going around the world and doing the politician, she's doing the scientist. So we celebrated in Florence a few weeks ago 20 years of operation of this institution, which is opened in 1998. Its peculiarity is being the first jointly operated laboratory between the two ministries in Italy. Science, that is the Institute of Optics, and Culture, which is the Opificio delle Pietre Dure. It was born by chance. We already cooperated with the Opificio since many years. We had our instruments there around the shop. Then they had the refurbishing of the Opificio, a lot of investment. And this room should have been the room for varnishes, varnishing objects. They discovered that according to safety rules, it was impossible to varnish in that environment. And so these 75 square meters of room were available for other things. And the other thing was an agreement with us for creating the laboratory of metrology, of optical metrology, inside the Opificio. And so we could start, I don't know why I'm using this. And so we started this cooperation, and initially it was not very, very good, because in 100 people and more in the Opificio, only 2 collaborators understood the importance of this. I can name them, Roberto Bellucci and Cecilia Frosinini, restorer and art historians. And we started from diffidence to synergy, as Lela put. So, that is about multidisciplinarity. You see why multidisciplinarity is needed, because it's a merging of the points of view that creates the good solution. Otherwise, the solution is partial. In this case, very partial. So we are pointing to transdisciplinarity with heritage science. And this model, I can say now, was created in 1998 when we opened that laboratory, because the laboratory was the chance for working with the people in the OP official, not for working for the people in the OP official. We started a cooperation based on a continuous day-by-day exchange over problems and solutions, and that was what worked. During 20 years, a lot of prototypal instruments were developed, tested, evolved, innovated using that laboratory in constant contact with real artworks, and more than with real artworks, with the real problems of artworks. That is more important. Typically, I have time to speak only of a few of that. Perhaps the most famous is this scanner for infrared reflectography, who was created well in advance, was first initiated in 1988 as a prototype by a group inside the Institute of colleagues. I joined the Institute in 1995, formally, and started cooperating in 1991. So it's not my not my medal, the creation of the infrared scanner. Anyway, most of the evolution I participated as software designer. And so we had in 2001 the first evolution, infrared plus RGB color. And then we had the first multispectral high-resolution reflectography in 2007. In 2011, we added a detail, the autofocus system, which proved to be a breakthrough. And in 2013, finally, we designed the actual version of the instrument, which is at 32 bands, half in the visible and half in the infrared. And these are images of the evolution. You see a lot of aluminum because it's very prototypal. There's also attempt to industrial version. For instance, these was the first attempt to an industrial version of the infrared color scanner. What is allowed by this instrument right from the start, the peculiarity of the instruments was to have a very good resolution in the infrared and a good geometry. So the image is not deformed by the fact that it is a scanner with a very wide scanning area, is 1 square meter. So the image of the painting is not deformed, even if this is a mosaic, but it is a mosaic of 8 images. So you can control deformation. And when you have a very good geometry, you can do things like this. That is the study of perspective done by Roberto Bellucci, using all the traces of drawing, underdrawing actually, that he found on this big panel. If you have the idea, the Annunciazione is not a small painting. And he found all the perspective lines used by Leonardo to draw this painting, and the preparation was not casual, because you see, this is the golden section. And it is repeated times and again in the perspective drawing. So what apparently is an image of an angel with the lady is perfectly a technical construction, mathematical in the details. So you can appreciate that art was technique and science in the Renaissance. Another thing allowed by this good geometry of the instrument has been a very important researches on so many authors about the use and reuse of cartoons, how the images were replicated. And so you can discover that some artists were more, let's say, pragmatic, and they used and reused the same cartoons times and again, probably to save time and money. Others were more creative, let's say. And you see that having different, having the images in good scale, you can play with this, and even if the transposition is not one-to-one, it was rescaled with a lot of techniques that they used at the time. Then if you rescale the image, you see that the image is the same, so it's deriving from the same initial cartoon. And that has created a lot of interesting discoveries in techniques of several authors like Piero della Francesca, Masaccio, and so on. Then we added the color layer, and this created a very easy use of the reflectogram because it allowed straightforward comparison with the imaging color, and so you could very easily see and compare what is 100 and what is over. Because most of time when you look at images of painting, it's totally different than that look at painting with the eye. You see a lot of things that with the eye you don't see. And there is the same for the reflectography. Maybe you see details in the reflectography and you think they are the drawing, then you compare the visible and they are not, because you can't see them. So anyway, analyzing reflectogram is a kind of an art. And so we just provided instruments for this art to be more effective. This is another example of the underdrawing in this very important painting attributed to Leonardo. Is still creating a lot of debate in the art history, because there is we could speak for this for 2 hours if we enter the problem of attribution of this painting. Then we added, with a trick, we added the 16 bands, and we started, practically speaking, multispectral reflectography at high resolution. This we realized by using a fiber bundle head. This is a custom fiber bundle solution that I designed years ago to allow the simultaneous acquisition of 16 channels instead of 1, without sacrificing anything, because even chromatic aberration and everything, if you use this bundle in the axis of the lens, the field is less than 0.5 millimeters, so you don't introduce significant aberration, and you have the possibility of scanning 16 bands instead of scanning just 1. And so you saw. The first version was totally devoted to infrared. And we had a version with infrared bands plus RGB. So we decided to get rid of 3 bands in the infrared to replace with RGB and obtain multispectral reflectography plus color. And this allowed very interesting discoveries like the Caravaggio, like the fact that the Last Supper is a turning point in Caravaggio drawing technique, because it's one of the paintings for which he drew the landscape, and then everything became black. So one of the first Caravaggio with black. But if you have good infrared, black is not black anymore, as it can be demonstrated on this Raffaello, which suffered more or less the same operation, this Madonna over a black background, but using the multispectral reflectography, we saw, you see that you advance the wavelength in the infrared, 1.4, 1.5, and look what happens to the ground. It becomes more and more transparent until 1.8, 1.9, you start seeing spolvero and architectural details. So this painting was not born with a black background, first. Second truth, Van Aspen and de Beer was wrong when he stated that 1.8, 1.7 is a good wavelength for reflectography, because there are things that you don't see unless you go to 2 point something. The game was successful, so we created a bigger one, and we had a custom fiber bundle, which is the heart of the machine, with only 6 fibers. We get rid of 4 because these are the yellow one. They are really far-field. So we get rid of 4, and we still use 32 bands, and we devoted 16 to the visible and 16 to the infrared. Things done with this version, this is allowing also color analysis, because this is kind of a spectrometer with fiber working on a plane of 1 square meter. And so it allows also color comparison in a certain sense. It was working on alchemy and monitoring the change of color during the cleaning process. This has been interesting because it's a total experimental operation on both sides. It's one of the first time the Opificio tried to restore modern painting such as a Pollock, so they learned a lot. And so everything was totally new, and this is very interesting to work together when you're practically doing research. Research on restoration, research on support to restoration. Another thing just to say, just not to finish with the infrared scanner, is microprofilometry. we created this microprofilometer several years ago with an optical head, integrated optical head, with quite good resolution. And one example of the use of this, apart from creating very good micro three-dimensional maps of painting, which are very useful for a lot of things, because you see everything. You see from retouchings to damages to cracks. You see a lot of details if you perform a microprofilometry on the surface of a painting. But this has been an interesting research case because it's kind of an impossible restoration. This was the last big panel restored in Florence, damaged by the flood in '66. It was thought an impossible restoration because the condition of the panel were horrible, because after drying, the wood planks shrank. And so that is the condition of the paint layers. Luckily, the big masters of restoration after the flood, they thought to use Japanese paper. Otherwise, all that would have been lost forever. But anyway, when the official tried to come to terms to this restoration, they found this situation. What now? And the first thing we did using profilometry is we tried to assess the amount of shrinking. So we used the microprofilometer on both sides, on the wood sides and on the paint sides. We produced profiles. And then with a very nice mathematical tools that I remember, but I don't have the time to present, we were able to dimension the shrinking of the panel considering the real dimension of the paint layer, which actually was made by gypsum, and so the paint layers didn't, the support of the paint layers didn't shrink, and so it was not more fitting on the wooden plank. So we measured the shrinking because we were able to stretch this profile back, first digitally and then by magic. That is exactly what the restorers at the officio did. They cut the panels and they stretched the panels and then inserted inserts just to regain the original width of the wood panels. And finally, after years and years and years of work, because the painting is also huge, they were able to inaugurate the last big restoration after the flood in Florence. So you see, technique sometimes is useful because you cannot do everything using tradition and craftsmanship. So this is our approach to heritage science and to conservation and restoration. Oh, thank you. Obrigado.
Thank you, Luca. I'm pleased to invite Professor Ado Jório for his contribution. Ado Jório Vasconcelos is a professor at the physics department of our university. He's also a former deputy director for research at the Federal University of Minas Gerais. Cleidson, vídeo? Não sei. Estamos tentando um formato.
So good morning, everybody, and thank you for the opportunity to meet a different community for me. So I have two different subjects that I brought here. As Luis said, I was, since March this year, I was Dean of Research in this university, so I have some information that are mostly institutional, and I think they are interesting for you. So this is one of the pages of the website of the Institutional Research Bureau in this university, okay? And if you, this is a list of the laboratories that we have in the institution somehow, okay? So the large numbers here, this is like humanities, more biosciences, multidisciplinary, and this is more like exact sciences, physics, chemistry, etc. So these are group laboratories. So we have on the order of 1,000 groups with their own laboratories. They raise the fundings themselves, etc. And we have other kinds of, this is laboratories for giving support to science. For example, a library is a kind of support for science, okay? And these are the institutional laboratories and centers for institutional research. And if you come to this website and you click on any of those, you will go to the website of this laboratory. You will find the website of our microscopy center. You will find the website of an imaging center in our biotech, our biology center, and laboratories like this, okay? And this is an effort of the institution to kind of organize the infrastructure that you can have access. And also, together with this, there is a lot of regulamentations and things for you, like how to have access. Of course, you can always have access to these places as an user, okay? So if you just find a collaborator and you want to work with this collaborator as a researcher in a group of these like 1,000 groups that we have, this is open like everywhere. If you want to go to some facilities, some of them you have to, like microscopy center, you have to pay for using hours in the microscopy centers. And in many cases, you can even have institutional agreements, okay? There are regulamentations that are from the university and from the federal government also. So we have laboratories in our university that they kind of, let me say like this, they belong to different institutions because you made an agreement, and this can be made with foreigners inside Brazil, and you have these possibilities, okay, to work in different ways according to regulamentation and law. So this is as much as I have for the infrastructure organization. Now I would like to speak a little bit more on a personal basis on the kind of research that I do. And I'm not on this field, okay? I don't work with this kind of science, but I work with something that could be useful. The laboratory I work is mostly devoted to optics instrumentation. So we have this laboratory. This is the web page. All we do is spectroscopy, is optical spectroscopy, but we have this, let me call Legoland philosophy, okay? So we don't have equipments that are used for something. What we have is a lot of optics, electronics, and pieces that we use to build instruments that we think are useful for something. And although we have never applied our projects to this field exactly, we have things that could be applied, okay? So one example I give you here is we work with the development of a technique that's called near-field optical spectroscopy, or that is more our real focus, is tip-enhanced Raman spectroscopy. So this is a technique where you join scanning probe microscopy that controls a nano antenna with a Raman spectrometer. And in this way, you can do Raman spectroscopy. You could also do luminescence, anything, okay? It's just that Raman is the most complicated, so we like the worst case, the worst scenario. You can do Raman spectroscopy with resolutions that go down to the nanometer scale, okay? And this is a cartoon, is actually made at NIST, and shows how this would be the resolution, so you get down to 10 nanometers, and this would be the kind of information that you have with the different characterization techniques. So we are developing this nano-optics instrument. It looks more like this, okay? So what you have is a home-built scanning probe on top of a microscope, and once you move this antenna that is nanometric, over the sample, you can have spectral information from things that are in the order of 1 nanometer. So we do molecular spectroscopy with molecular resolution. Here is a very different scale, let's say, is we are developing a system that is a laser scanner of the retina of a human being, okay? We are still working with mouses, okay? But what you have here is, oops, sorry. What you have here is fake, okay? We just put a professor and a student there, but it's not up to this stage. But the idea is that you will see the back of the eye of the person, and the laser will scan and will provide back the Raman, fluorescence, etc. spectra of the back of the eye. And this project is devoted to identify beta amyloid, that is a peptide that is related to the development of Alzheimer. So we will have a scanner that identifies specific proteins in your retina or anywhere in your eye, okay? Here is, again, a more realistic cartoon of what you have, and this is a mouse that is being scanned, okay? And this is a Raman image of a beta amyloid in the retina of the animal. Okay, and so before we were looking into nano objects, trying to develop spectroscopy to that level, and here we are more like trying to access hard places with optics, okay? So in general, we think this could be useful somehow. And as a last piece of let's say, the work that we do, and here is less on instrumentation and is more on a case that I think could maybe be the closest study that I have from your interest, is we have these, in Amazonia, we have the so-called Terra Preta de Índio, is the Indian black earth. So we learned after anthropologists did some research that the Indians, before Columbus came to Brazil, the Indians used to change the soil, to improve the soil for agriculture. So the Amazon soil is very poor, as most of the soil in the tropical region of the world, because of high temperatures and rains and etc. So it's very bad for the stability of organic matter. But the Indians, they developed a very specific way of burning trash and add this to the soil to transform the usual soil that's very much like this, is very sandy, into a soil that's black because it's full of carbon. And this soil is very, very stable for agriculture in general, okay? It retains water for a very long time, and it keeps organic matter in a better way. And what we did here was analyzing the structure of, using Raman spectroscopy, analyzing the structure of this carbon material, and we learned that, of course, they didn't know at this level, okay, but they learned somehow to burn organic matter, to burn trash, making material that has the right size of the nanoparticles in the carbon material, that if they were bigger, they would be inert, so they would not be good for agriculture. If they were smaller, they would be unstable. So they learned that there is a burning process that makes the material stable, but at the same time able to exchange cations and anions. That's important for agriculture. So this is what I have to show you here, and I will be happy to answer questions.
Thank you. Yeah, before we move on to, hold on just a second. Before we move on to Marco Wopalensky and no, to advanced, to Michael Vopalensky and Carla Bauswaite. Professor Jório will have to go soon because he has other commitments and family commitments, which, right, the kids. So I will close this session between Luca and him, and then we continue, okay? So if there are any comments, I'd like to emphasize the importance of the work described by Luca, please. Yeah, because if there are questions, we close them now, and then we move on to the other ones. Okay? Yes. Because then we'll move to advanced diagnostics for intervention in conservation, 3D tomography, and Professor Carla Bauswaite and Michael Vopalensky will speak. Thank you very much to both for your intervention. Thank you for showing the result of the work of the Deputy Director for Research, because this is really going to be very helpful for, this is already very helpful for us for guiding our work. And the floor is open. Please. Professor Carla Bauswaite.
Hi, Ado. Just a curiosity. Do the Indians still know how to burn it, or is that knowledge lost?
So the sites that people know, they are mostly located close to rivers, and they are not populated anymore, let's say. And the sites that people study, they do aging, and they all belong to tribes that, like, they did that soil like 500 years ago or more, okay? So, but this is very close to the rivers. It's, there is very little knowledge about the real interior of the Amazon. So I cannot answer, I cannot say yes and I cannot say no. Okay.
Professor Bruno Brunetti, University of Perugia.
It's a question for Ado, yes. We had some experience with CERTS, but not with tip-enhanced Raman spectroscopy. And you mentioned that you did some experiment in this sense. Also, Dalva mentioned this technique that is extremely interesting. It is one of the techniques of the future, I think, applied to cultural heritage. So can you say something more concerning this? You mentioned an antenna that you move, so the tip works like an antenna and can achieve also resolution at nano level. And did you have direct experience? What do you think? Is the reproducibility good in this sense, or there are some problems? What are the perspectives? So thank you. Yeah.
So the perspectives are really good because, well, yes, I was never an expert, and I didn't work a lot on CERS. I did work a little bit. Maybe I have 2 or 3 papers on CERS. And of course, the difference here is like if you could control the position of the hotspot. This is the, I would say, the best part of TERS with respect to CERS. And on the beginning, TERS was very, how to say, it grew a lot after the 2000, okay, in the last 15 years. And on the beginning, the tip was, the production of the tip was very, some tips work, some not, some gives a good enhancement, some doesn't. But now there is a new process where you make the tips using the silicon technology that people know for, you know, we have computers, etc. So the tips today, they can be produced in mass production on a very high quality. And they developed in a way that you generate with silicon patterning. You generate a plasmonic edge that couple very well with the laser. So the reproducibility of the TERS is getting very good. And with this, the enhancement, the resolution is, the most impressive result that we have today was published the first time in 2013 from a group in China. And they imaged a molecule with resolution close to angstroms, like an STM. So it's really, it's getting to a point where it will be important.
So thank you both. Thank you very much for your contribution. So let's move on to the next session entitled, the title is Advancing Diagnostics for Intervention in Conservation, the 3D Tomography and Additive Manufacturing in Archaeology, which will be presented by Dr. Michael Wopolensky from the Czech Republic, please. And then we'll move on to Professor Carla Balswaite from the Microscopy Center of the Federal University of Minas Gerais. Quer? Não, já está ok, está tudo bem. Everything okay?
Good morning, everybody. I'm in a strange situation because I was asked to prepare the presentation in Spanish, and I did it. But now everybody here is talking English, but I have the presentation in Spanish, so I will still do it in Spanish, I think. Bueno, entonces yo voy a continuar en español. Yo quisiera solo decir un par de palabras sobre mí. Entonces, lo más importante es que estoy trabajando ahorita en el laboratorio de la tomografía computarizada por rayos X en la ciudad de Telč, en Centro de Excelencia que pertenece a la Academia de Ciencias de la República Checa. Y estoy muy feliz por estar aquí. Es mi primera vez en Brasil. Estoy encantado con eso. Me da mucho gusto y mucho honor. Y la verdad es que a mí siempre me ha atraído Latinoamérica, y entonces yo pasé casi un año en México, y ahora tenemos ya algunos proyectos con los mexicanos de la Universidad Nacional Autónoma de México que no tienen mucho que ver con el patrimonio cultural, son más como de biomedicina, pero pues ya se estableció alguna cooperación. Bueno, entonces eso es la foto desde anteayer, desde hace una semana. Ayer tuvimos menos 12 grados, entonces yo estoy por eso también bien feliz por estar aquí. También involucré un folio sobre la huella checa aquí en Brasil. Entonces, Juscelino Kubíček era de un origen checo, o sea, su mamá era de origen checa. Kubíček significa, es un diminutivo de Tiago, porque Tiago es James, ¿no? James, Jacobo, en checo Jakub, y Jakub luego se dice como Cuba, y el diminutivo es Kubík o Kubíček. Y entonces él viene de Bohemia del Sur, y ahora ya dije la palabra Bohemia, y entonces cuando yo fui a un supermercado aquí, para comprar el acoplador de la electricidad, ahí me fijé que también tienen esta cerveza Bohemia, que obviamente es un nombre de cerveza muy popular en el mundo, porque también la tienen en México, y hasta que yo sepa. ¿Y qué es Bohemia? Pues Bohemia es el nombre de los países checos histórico, porque lo que ahora es la República Checa, entonces aquí estamos. Y lo que es República Checa originalmente eran, 3 estados, Bohemia, Moravia y Silesia. Pero Silesia es grande y nosotros ahora tenemos solo una pequeña parte de Silesia. Entonces Bohemia es realmente el nombre histórico del estado donde está Praga, ¿no? Perdón. Bueno, un par de palabras de la estructura de investigación en Telč. Entonces, Telč es una ciudad en la República Checa aquí, ¿qué quiere decir? Que está en la mitad entre Praga y Viena, más o menos. y nuestro centro es muy nuevo, es que se abrió en el 1 de enero de 2014 y tenemos ahí ciertos grupos importantes de investigación. Son laboratorios de análisis de materiales, luego una unidad para sostenibilidad del patrimonio cultural, laboratorio de diagnóstica móvil y el túnel climático Vicente Strouhal, y laboratorio de tomografía por rayos X, y yo soy el jefe del laboratorio de tomografía por rayos X. Aquí se ve el centro, entonces se anota que es nuevo, y aquí vemos Telch. Telch es una ciudad de renacimiento, está protegida por UNESCO, es muy pequeña, tiene como 5.000 habitantes, pero es un buen lugar para trabajar, o sea, bueno, depende del gusto personal, pero es un poco diferente que trabajar en una ciudad grande como en Praga, que no es tan grande comparado con las ciudades latinoamericanas, pero bueno, ahí hay mucha naturaleza en el alrededor y entonces la vida allí es muy tranquila y muy buena. No voy a hablar mucho de rayos X, solo para, bueno, un poco decir que todos sabemos que rayos X son rayos de la radiación electromagnética que tienen la longitud de onda pequeña comparado a la luz visible y que Konrad Röntgen también tuvo el honor de obtener el premio Nobel primero en física. En la radiografía de rayos X no se utiliza mucho la óptica como en los sistemas ópticos, pero los tubos, los generadores de los rayos X, ahorita, en esos tiempos, son usualmente cone beam. Eso significa que el beam es un cono, ¿no? La radiación se está distribuyendo en un cono del tubo. Y entonces, si quiero hacer una buena magnificación de objetos pequeños, les puedo estacionar cerca del tubo, del fuente de la radiación. Y si tengo objetos más grandes, los estaciono, los pongo más cerca del detector. Y por eso es muy importante que tenga la posibilidad de cambiar esta geometría en el equipo. Bueno, luego que si quiero hacer la tomografía computarizada, eso significa reconstruir volumen 3D, el modelo 3D, primeramente hago proyecciones. Nosotros normalmente hacemos como 2.000 proyecciones por una rotación. Entonces es mucho. Y luego de estas proyecciones, por algunos trámites matemáticos, se puede reconstruir el volumen. Entonces, ahora estoy hablando de algo que supongo que todos conocemos. Ahora con el volumen, claro, porque los rayos X penetran a través del material, podemos también ver lo que está dentro, que es muy importante. Eso es la tomografía computarizada de medicina. Lo estoy enseñando aquí porque es claro que en este caso es necesario mover el tubo y los detectores porque no se puede hacer vueltas con el paciente, ¿no? O sea, tal vez se podría, pero no se hace normalmente. Y nosotros, y pues los tomógrafos industriales, se pueden dar el lujo de dar vueltas al paciente, o sea, objeto. Y entonces, desde el punto de vista de construcción, es más sencillo porque el detector y el tubo pueden estar fijos. Y eso es nuestro tomógrafo que tenemos ahí en Telch, está patentado, se hizo ahí de los componentes, entonces no está comprado como una obra lista. Y ahí tenemos dos ejes de radiación o dos fuentes de radiación que son perpendiculares. Entonces llamamos a este equipo Toratom como Twin Orthogonal Adjustable Tomograph. Y lo que se anota, y tal vez aquí se anota mejor, que tenemos 13 ejes de movimiento. Entonces podemos influir la geometría mucho. Y eso es importante porque ya regresando a otro slide, sabemos que con la geometría podemos también influir la magnificación y por eso también la resolución. Entonces, lo más pequeño que hacemos son huesos humanos o también bovinos, buscando microfracturas en ellas, y esos huesos tienen diámetro, o esas probetas tienen diámetro de 1 milímetro o algo, y la resolución ahí está cerca de 1 micrómetro. Mientras que también podemos medir estatuas que tienen 1 metro y pues el diámetro de 40 centímetros, digamos. Bueno, y ahora algunas aplicaciones para el patrimonio cultural. Lo que hacemos muy frecuentemente es el análisis de porosidad, porque se utilizan varios como que tratamientos químicos ahorita para las fachadas que sufren por, bueno, las influencias climáticas, claro, ¿no? Entonces, lo que aquí se ve son algunas probetas de fachada de una ciudad también protegida por UNESCO, cerca de Telch, y una está tratada con algún medio para protegerla y el otro no. Y entonces ahí se dejó por 1 año y luego se hizo una comparación. La porosidad en 3D es una cosa muy interesante y hasta ahora no hay muy bien desarrollados métodos para como que describirla, porque normalmente la porosidad se hizo en secciones en el microscopio y entonces se también definieron las figuras como ovalidad y estas cosas, pero en 3D, eso por ejemplo, eso que es aquí, que es rosa, es un poro, está interconectado dentro y entonces no puedo hablar sobre la ovalidad o esfericidad de este poro, ¿no? Entonces, eso nosotros no interpretamos. Nosotros hacemos la tomografía, pero la gente que luego lo interpreta a veces está así confundida en la cabeza como tomarlo, ¿no? Como hacer de esto algunos buenos resultados. Pero bueno, se hace y por lo menos podemos decir cuánta fracción es el aire y cuánta fracción, o los poros y cuánta fracción es el material. También hacemos la radiografía de pinturas, entonces no tomografía, sino radiografía, porque ya que nuestros ejes están movibles, podemos escanear una pintura con mucha o muy alta resolución. Entonces aquí en esta pintura, por ejemplo, el volumen el área de la pintura escaneada era de 66 megapíxeles con la resolución de 100 micrómetros per píxel. Aquí se ve cómo se fija la pintura dentro del equipo y eso es María Teresia, ¿no? la emperatriz de Austria-Hungría. Y lo que aquí podemos ver es que originalmente su cabello era en este lado y aquí se anota un poco el tercer ojo, o sea, el ojo original. Entonces se supone que no le gustó la pintura o algo así, y entonces se tenía que repintar, ¿no? Y eso es muy importante para los restauradores, claro. Aquí tenemos una obra de madera del siglo XVI del maestro IP, y nosotros hicimos también la tomografía y el propósito originalmente era ver los, ¿cómo se llaman estos? Los círculos en la madera, ¿no? De los años. No sé cómo se llaman en español exactamente. Pues. Bueno, anillos de crecimiento. Gracias. Y entonces, basado en estos anillos de crecimiento del árbol, también se puede, por la dendrocronología, hacer una datación del objeto. Pero en este caso particular no se podía porque si se va desde arriba abajo, pues no hay tantos anillos de crecimiento para poder analizarlo pues bien y sin duda. Pero bueno, el propósito original fue este. Y luego también lo hicimos para saber de cuáles, o sea, de cuántos pedazos de madera está hecho y otras cosas. Eso también es de Galería Nacional Checa, es del siglo XV, una pintura en madera. Y aquí se anota algo que normalmente no vemos, que aquí hay mucho más pigmento que aquí, que significa que en el pasado, obviamente aquí había algún tratamiento de restauración. Bueno, eso voy a resaltar. Ajá, tenemos una cámara, es esta, que dentro tiene un chip, un detector espectroscópico. Y entonces lo que se hace con un chip de XRF, ¿no? Esta fluorescencia de rayos X, normalmente allí hay solo un chip. Aquí en este chip tenemos 256 por 256 píxeles y entonces podemos hacer un mapa de lo que ahí tenemos. Entonces en este caso, por ejemplo, aquí se ve cómo está mapeado la composición en el modelo 3D de tomografía. Es bueno, pero la resolución energética de nuestro detector no es muy mala, no es muy buena, entonces ahora estamos construyendo un nuevo equipo con mejor resolución, porque por ejemplo el 5 y el hierro no podemos distinguir con nuestro equipo ahorita. Aquí se ve una estatua que hicimos hace 2 semanas, la verdad, por el mismo propósito. Entonces, hacer un análisis de composición en la superficie de las pinturas. Esta estatua es de madera y es muy antigua, es del siglo XV también, entonces es bastante preciosa también. Y lo que vemos por la tomografía, que se hizo en ciertos pasos, en como 5 pasos de la altura, gracias a la variabilidad de nuestro equipo, son por ejemplo estas cosas. Entonces dentro de la cabeza hay algunas, algo de hierro, algunos clavos, o algo que desde afuera no se ven, ¿no? Y aquí, bueno, en la pantalla esta no se anota, pero aquí se ven bastante bien los círculos o los anillos de crecimiento, entonces tal vez se va a poder también hacer una dendrocronología. La resolución en este caso fue como 0.1 milímetros por voxel, pero siempre la resolución también tiene algo que ver con la magnificación. Entonces, si tengo un objeto grande, bueno, no puedo esperar que voy a tener una resolución grande porque siempre depende del tamaño del detector y yo necesito que el objeto esté en el detector en todos los ángulos. Hasta que en este caso no se podía, entonces hicimos una tomografía de ángulo limitado y con eso podemos hacer tomografía de un objeto que tiene en diámetro como 60 centímetros. Esta estatua tenía 40 y algo. Pero aún eso, la resolución en este caso pues no puede ser un micrómetro. Bueno, solo muy brevemente, eso es una parte de órgano y hay muchos órganos, claro, en la República Checa y bueno, en la Bohemia Central, en las iglesias, y también están dañadas por estos bichos de madera y luego hay fugas, ¿no? Y si hay fugas en órgano, pues no es nada bueno, ¿no? Y entonces nos preguntaron si podríamos ver dónde están los túneles estos hechos por este insecto para poder inyectar algo en los lugares donde hay fugas y no se ve porque están dentro y están interconectados 2 canales de aire a diferentes tonos, a diferentes tubos. Y entonces lo hicimos porque pues no era bastante claro que si se va a ver o no, pero sí se anota, ¿no? Sí se ve bien. Y entonces algo que desde afuera parece más o menos bien, ¿no? Aquí se ve que está totalmente comido por este insecto, ¿no? Otra aplicación para órganos es cuando se hace restauración de los tubos, se tiene que seguir también la composición del metal y estas cosas, pero también estos ángulos y todo eso se llama el núcleo del tubo. Y eso no se puede medir desde afuera muy fácilmente y en los rayos X tenemos la respuesta en unos segundos. Aquí está un ejemplo de la actitud multimodal, o sea, multienergía, que aquí ya hoy se estaba discutiendo, pero no para rayos X. En rayos X también se puede utilizar. Por ejemplo, eso es un manuscrito, bueno, eso es una probeta que nos hicieron en el Archivo Nacional, pero está hecho con la tinta histórica que contiene hierro, ¿no? Pero las capas de hierro de esta tinta son muy delgadas comparado al papel. Y entonces, en la tomografía normal o en la radiografía normal casi no se ve la letra, ¿no? Pero podemos hacer la radiografía o tomografía en dos distintas energías y luego con el tratamiento matemático que básicamente es una sustracción con ciertos coeficientes, podemos visualizar bastante bien la letra. Eso puede tener mucha importancia para los archivos donde tienen muchos libros que ni quieren abrir, pues no, claro, porque se pueden dañar con esto. Esto es una tabla hieroglífica y yo tengo una copia, no de esta, de una otra, hecha en la manufactura aditiva, entonces la voy a dejar aquí para pasar. La hicimos en México, entonces es un ejemplo de la cooperación con Latinoamérica. La cosa es que en ciertos tiempos las tablas hieroglíficas estaban envueltos en barro, que ya no estaba quemado, pero estaba así envuelto en un sobre de barro. Y entonces no se ve que está dentro. Para un arqueologista o para un arqueólogo ya es una maravilla que puede venir con una tabla de este tipo. Y nosotros hacemos la tomografía y virtualmente en el modelo 3D le quitamos el sobre y él ve que está adentro. Ya eso es la maravilla. Pero si luego le podemos hacer una copia uno a uno en la manufactura aditiva, es algo que pues les quedó sin palabras en la primera, bueno, al concreto arqueólogo, porque él no sabía de estas tecnologías. Bueno, claro que muchos saben. Y él dijo, pues no es posible, no, eso que me dicen, pues no es posible. Y nosotros entonces luego en México, en el laboratorio de manufactura aditiva, en la UNAM, con mis compañeros, hicimos un ejemplo de la utilización de esta técnica para arqueología. Y eso es importante desde el punto de vista de infraestructuras que ya aquí hemos discutido, porque eso es un ejemplo de la interdisciplinaridad, ¿no? Que es una tecnología que no tenía nada que ver con arqueología antes. Y ahora, bueno, para arqueología puede tener mucha importancia porque hacer las copias para museos, por ejemplo, de algunos artefactos, pues cuesta mucho trabajo. Y si tengo ya los datos 3D, los modelos, pues lo puedo hacer así, pues en cientos copias y pues venderlo en la feria, ¿no? Pues es claro que es mucho más fácil. Yo no sé cuánto tiempo me queda, como menos 5 minutos. No, bueno, voy a hablar rápido. Ese es un amuleto de plomo. Es que se utilizaron esos amuletos en las tumbas desde los tiempos romanos y hay una que se encontró en la República Checa, en los países checos, apenas, que se encontró hace 5 años o algo, y es de plomo. Y en Alemania, en Heidelberg, tienen como decenas de estas. En toda Europa se han encontrado algunas, pero en total yo creo que ni es un ciento de ellas. Es bastante rara, es una cosa bastante rara. Y ahí lo abren y lo leen. Y ahí normalmente ya en los medios tiempos hay algo de la Biblia o algo así. Está escrito en latín y en Escandinavia en runas, ¿no? en la letra de runas. Y entonces los que lo encontraron en la República Checa no querían abrirlo, no querían así pues abrirlo porque ya pierde su valor, ¿no? Y entonces nos pidieron que si no se puede hacer tomografía de esto. Pero es que hacer tomografía de plomo es como hacer el agua arder, ¿no? O sea, no es tan fácil porque plomo se utiliza como una cosa contra los rayos X, ¿no? Pero nosotros lo hicimos y después de mucho procesamiento se podían visualizar las letras y luego estuvimos como que separando una capa tras otra y entonces puedo decir que ahorita, hasta que sabemos, este amuleto es el único en el mundo que está leído y no se había abierto. Entonces preparamos ahorita con Viena y con el museo, con un museo preparamos algún artículo grande pues, sobre esta cosa. Eso creo que puedo resaltar. Era un encuentro de algunas monedas y claro que los arqueologistas quieren saber cuántas monedas ahí están y, pues, y de qué tipo y esto, pero se pueden imaginar cómo funciona. Luego aquí hay una sección, entonces ahí hasta que se puede leer qué son. Y aquí tengo dos últimos ejemplos que hacemos para la arqueología. Esta cosa, pues no sé cómo llamarlo bien, son los restos de espadas o de artefactos de tiempos celtas en Europa. Entonces eso quiere decir como, yo no sé, 500 años antes de Cristo, ¿no? En Europa. Y es que está corroído y mucho, y entonces pues no se ve nada, pero luego la corrosión no tiene tanta atenuación como el hierro compacto. Y entonces nosotros hicimos ahí la tomografía, aquí se pueden ver algunos detalles en la vaina, pero que es más importante en este caso fue esto. En una espada, ahí en ciertas secciones aparecieron estas estructuras, que muy probablemente es algo engrabado por allí, alguna decoración. Se anota también aquí. Aquí se ve que hay algo que a duras penas será corrosión. Y entonces ahorita el modelo se está analizando en Sorbona, en París, porque ahí tienen un grupo grande para celtas, y entonces ahí trabajan con nuestro modelo y vamos a ver qué sale de esto. Aquí se ve cómo se hace la tomografía de otra vez, pero pues lo podemos imaginarnos simplemente, yo creo. Entonces ese es un ejemplo, pero lo que es más importante tal vez es que de una cosa que está totalmente corroída, ¿se dice? Fernando, corroída. Luego, que si todavía hay algún hierro compacto dentro, se puede reconstruir el núcleo, digamos, del objeto. Y entonces luego se anota cómo se hizo y pues cómo parece, digamos, ¿no? Bueno, ahora no sé a dónde regresar. Ajá, aquí. Bueno, eso vamos a resaltar. Y la última cosa que quiero presentar es una puñal del tiempo de bronce. Entonces tiene como 4.000 años y se encontró en un campo hace 3 años, casi exactamente hace 3 años. Y nos llevaron esta puñal y querían saber que si allí detrás de la vaina, que si también hay alguna decoración, algún engravado. Aquí se anota un poco, pero no mucho. Pero bueno, sí hay un engravado en, en esta parte. Y de esto hicimos un video que se ve, yo digo, muy bien, entonces por eso quería presentarlo como mi último slide. Entonces luego le pusimos algún color de metal, ¿no? Para que se vea más bonito. Aquí está el puñal desde detrás y lo que ahora podemos hacer es esto. Y ahora se anota que también desde este lado tenemos la decoración engravada, ¿no? Nos dijeron los arqueólogos que este puñal definitivamente no es de la República Checa, que se hizo en la costa báltica y que lo trajeron a la República Checa probablemente por la ruta de ámbar, que había una ruta desde norte al sur de Europa, la ruta de ámbar, y entonces cerca de esta ruta se encuentran algunos artefactos arqueológicos. Ahora vamos de nuevo por las secciones y regresamos. Y ellos, basado de este modelo y de la tecnología como se hizo, podían entonces decir que es báltico, ¿no? Que ahí se hizo. Ajá. Y bueno, entonces, gracias por su atención. Espero que les haya gustado. Bueno. Y quería decir que aquí dejo algunos newsletters del instituto. Si alguien está interesado, pues puede tomar algo, ¿no?
Professora Carla Boswaite, please. Muchas gracias. Yo también entonces voy a hablar en español. Professor Boswaite is a colleague of us from the physics department, and she's one of the professors running the microscopy center of the Federal University of Minas Gerais, which is a multi-user facility.
Good morning, everybody. I'm going to talk a little bit about tomography, not so nice images as Michael, and because we are at the very, very beginning, and I hope that we can increase our collaboration. So I'm going to tell a little bit, well, why tomography, maybe just an overview. The main idea is to access volumetric data hidden in some form. And the main reasons is to gather information, but also to register. And for reproduction, also, as Michael said, maybe selling in the fair. So, and the type of data we can access, normally the first one is, of course, morphology, but we also can have chemical data and structural data. And some ways that it's all over the internet, that's a replica of a small statue that was acquired with X-ray tomography and just 3D printed. The idea is going from a projection, as you see, that's I got from Paul Midgley, which in electron tomography is one of the fathers of the technique. You have a just an object, a bunny here, and when you project it, you see a hand. So the projection is not straightforward to reproduce exactly what I'm seeing. So tomography is not a straightforward technique. And then I just, that's a courtesy of Zeiss. I don't know if you will identify what that is. It's quite nice. It's just play around what they did. Does somebody identify what it is? People who have kids? Yeah, Kinderovo. So it's just, you see, without opening it, you can see the small animal which is inside the egg. So it's just, well, quite nice for just playing around, but you have an idea what you can do with that. And with 3D tomography, we go back to radon, which has the first algorithms that are used for tomography, any kind of tomography we have now. And oops, I'm doing the same. Okay. We can have non-destructive techniques, which lasers, visible light, X-rays, electrons, neutrons, and we have also destructive ways, which for cultural heritage are not interesting at all. That's just for material science on some specific problems where you can destroy the object you want to acquire. And nowadays, it's being getting more and more interesting, the additive manufacturing, which the definition is a layer by layer construction, but essentially you can think on a 3D printing. And what people are doing, you have seen the model by Michael in kind of plastic, but people also have been working on metal, concrete, ceramics, and different kinds of materials, so that's getting quite interesting. And a normal tomography workflow, we have a 3D object, and you acquire. Normally in tomography, a tilde series, or that's traditionally, we have been, people are working on algorithms that you can use different geometries. Then you have a whole bunch of processing that you have to align those layers and stacks. And then you have a processing to have the end model, so it's a lot of mathematics and a lot of computing that is behind that. And the ideal situation, what we say, is that you have as much information of the object. That's what I'm just using Michael's lecture, not to have, instead of turning the person, to turn the object as much as you can, so you can get the information needed. You have also different geometries, as I said, and here thinking about what Anna said, that instead of scanning, that you can have some techniques maybe in the future that you can have just one detector and get everything, all the information, and by smart thinking and analyzing, maybe you can do something like that. And here we have a specific problem, again from a lecture of Paul Midgley, is that is known in electron microscopy that people do a lot of tomography already, what we call the missing wedge, because we turn the sample and we are not able to turn the sample 360 degrees. So you lose information, and here is a nice picture that here would be the original image, and here if you go only plus minus 20 degrees, plus minus 40, or plus minus 60. So you have missing information around there that you have to get that into account when you are reconstruction something. The main strategies is just on the acquisition that you have, thinking what Dalva said, you have to think about your problem, how you want to solve, or what do you want to solve, and then you will have to work on those strategies. What kind of radiation and what kind of object. Of course, I cannot put a sample like that in an electron microscope, just very tiny samples. A lot of aligning. and several reconstruction algorithms that are more specific for types of acquired images, and you have to work at that. And the modeling also, which when you have done everything right, we hope that you can have a reconstruction of what you really had there. And here are some examples. That's again from ProMidgley that they were thinking about. Here you have 50 nanometers on shapes, because if you have just a 2D projection, you cannot identify that you really have the same thing. So you end up with a lot of different morphologies, and then you think, well, it's exactly the same. And that has been creating a huge revolution in the biological area, because normally in electron microscopy, you just had a projection of something. And now you are able to reconstruct a volume, and then you identify, well, that's the same thing, just seen or projected in different ways. And here you can see you have a triangular shaped thing with a certain thickness, and you have different angles that you can see a projection of the same thing. Here say this is equal to that. It's the same object, just turned in a certain angle. And here, that's a small image that we did some time ago with a sample from a professor of the chemistry department. Here you can see just the reproduction of the layers. And so you see it's a lot of things, colors, gray color that you cannot make out anything. And that's your starting images. And here you have the actual, oops, come on. Nope. Tired. Yeah. No, I can open it later on. I think it's just, let's see if Microsoft works some way. Reset. Yeah, okay. I can show it. Oops, did it? No. Well, it should be turning, but here I wanted just to show you one small problem that we had. It's as it is a nanoporous alumina, it's not crystalline at all. So it has intrinsic error in interpretation, because we were not able to align the stacks. So you see, you have empty spaces here which are not possible. It should be connected. So you see that there is a lot of things. It's not a straightforward thing, because we did not have anchoring points on there. And then you end up with something, and you say that doesn't make sense. Okay. That's again of Paul Midgley, and that's something that we have. It's a problem in many samples nowadays in nanometric scale. You have 20 nanometers, that's you have particles inside another structure, and you want to see the particle distribution. So when you get your tomography here, I have both morphological information plus chemical information. You can just digitally remove your structure and see the particles, count the particles, measure porosity, so you have access to the internal structure over there. And here one word, it's uses tomography, and that's something that if everything goes right, we'll have a professor from Ireland over to start teaching us, which we call electron crystallography, which is identifying known and unknown phases in the nanometric scale for heterogeneous materials, or if you have something very, very small. And it's one of the techniques which uses tomography, but also precession. So we use the diffraction patterns, and here you can see just, I think it's time to explain, it might be a little bit too much over because it's quite a large thing. But the important thing is that the number of information you have when you use or precession. Precession means I'm going to turn my sample, but I'm also going to make the beam move. So it's a little bit more than just tomography. They are writing scripts for using tomography also, or for using rotation, so there is a lot of things going on. But the important thing is that you have access to much more information. Here you can see a limited amount of diffraction spots. So here you see increase in the amount of diffraction spots. And the interesting thing is that as we have a very strong X-ray community in Brazil already, and Carlos Basílio, which presented yesterday, is an X-ray crystallographer, we have many similarities, so we don't start from the scratch, but we already built or we work together to implant electron crystallography here, and we'll be able to find the structure, that's what I call them structural information, is where are the atoms in my material, and so to be able to identify what I have. So I hope that we'll start soon on that. And that's a picture I enjoy a lot, and it's one picture, not exactly that, but the book of Williams and Carter, the basic book for material science and transmission electron microscopy, he uses that, is that you have to be careful of what you are seeing. So, what they say in Williams and Carter, normally, if you look at that, you say, well, that's not possible. But if you look onto a microscopic image, a lot of people are seeing that and not even being aware that they are seeing that. So working together is very, very important, especially when you interpret your data, not to misinterpret it, and that's it. Just to know, does it make sense, yes or no? So that's very, very important. And that is part of the work that we are starting with Carlos. Juliana is a PhD student, and Max is a postdoc. And we are starting on meta-organic frames, but the idea is to have that for all other types of techniques, and we can maybe work on optical imaging maybe in the future, just using what we learn with the methods here. And the meta-organic frames it's just an organic thing. It's a lot of carbon, oxygen, and hydrogen linked with a kind of metal. This material is zinc-based. And the idea is that playing around with how you synthesize this material, you can open up and increase and decrease the pores. And it's a material very similar to zeolite, which also have pores, and the idea is to use it for several applications, from catalysis or energy storage or whatever. So we are just at the very beginning. And that's how they look. So we have platinum nanoparticles around 1 nanometer, the smallest ones. The bigger ones do not interest us. But we want to know if that's inside the material. And as we have a projection, we don't know if they are outside or inside. So the idea is to try to do tomography. Those particles are those small, very dots over here, almost difficult to see. But one of the problems is that's the beginning and that's the end of the sample, so it's beam sensitive. So we are struggling with something before, and I'm going to try to reconstruct that anyway. We just made some measurements at the microscope of LN nano because we don't have the resolution here for that. And there is starting a work together with people from LN nano also in the future. And so I'm going to talk a little bit about possibilities very fast also because time is going on and we have a session in the afternoon. And there are some possibilities that I just put it like that. Let's see if it goes. That's a lab. Oh, well, I put a link there, so I did not test if the link was working. It should, because it's not a file. Anyway, Professor Elmo is just over there. And it's the second project of him, which I'm very, very glad, because I make use of the first project of him a lot, which is a demonstration room, which has one of the ideas is just to develop material for people, for the professors at the department, to use as demonstrations for their classes. And this project now is a second one, which just was born at the demonstration room, where they are building other things. And the last thing, which was very, very nice, they are building atomic force microscopes using parts of the CD player as the optical part. And they have been having very, very nice results. So the idea is that we have just a collaboration with building sensors or trying to work on the MoLab more, and maybe making other things around. So I think he has about 60 students on the waiting list every semester. So there is a lot of keen guys to work. And they already have one small 3D printer. So we don't start from the scratch also on that. So small objects we are already able to build. They are building things for making equipment there. There is a second way on 3D printing, which is Professor Eduardo Valadares, which is very nice. And then we have started talking with people from the astrophysics group and statistical physics group, especially to help with all the computing. They are a very strong programming people, and they work already on Linux and Unix-based calculus, so they have the knowledge, and we might profit from their expertise, and also a very strong computer science department, which probably we have to start talking and see who is interested in collaboration. So they have very, very interesting people around, and very young people also. That's just a model made by Professor Eduardo's lab. It's fullerene, and it took, I don't remember, it said some months to build, but it's a very nice replica with the angles and the atoms in the right place. Just something which is angstrom sizes. You can see that you can do much bigger, so that's quite interesting. And just the last slides, some words of the Center of Microscopy, which was born multi and inter and transdisciplinary from the start. And it's just open for everyone. It has a multidisciplinary management also. We are people from the whole university. Luis was at the beginning of the project also involved. And that is the site, so anyone who needs to have access can go there, submit a small proposal, so for us to see if it's feasible with the equipments we have there. Sometimes we need to go somewhere else, like to LN Nano or whatever. And that's an overview of the equipment, sample preparation labs, and thank you. And I always like to list our funding agencies, because without them, we just don't work. So thank you.
Thank you very much, Carla. May I invite to the table Michael Vopolensky. Oh, Carla, please stay. Because of the commitment to start our session precisely at 1:30 after lunch, I've discussed the matter with Luca, and we will move the presentation by Fernando and Michael about education and training to the late to afternoon, okay? So I'm opening, because of the time, I'm opening the floor for questions, and then we go for lunch. So thank you very much for the presentations. The floor is open. Please, microphone.
I don't have a question, but I think it is interesting because of this panel about tomography to add some information about other groups in Brazil. We have many groups in Brazil working on tomography in the last decades, and especially on cultural heritage. There are two groups that are working the last 10 years, about 1 decade, using tomography and the microtomography on cultural heritage. For example, working on the structure of archaeological ceramics, the profile of the porosity, the profile of porous space, the profile of the additive that the indigenous people used, put in the ceramics, studying the engobo layer, and a lot of characteristics of the technology of making the archaeological ceramics. Just to be brief, I think that the people must know that. Okay?
Where?
One group is at Rio de Janeiro, at COP, at the Instrumentation Nuclear Laboratory, and the other one is in Londrina. We work with tomography in the last decades, and especially with archaeological ceramic in the last years, using very different device, to be short, but we can talk more, okay?
Any other? So thank you very much. Hopefully, there are several issues here, several research lines and possibilities that, as we move along within our plans to grow and to have more participation of other research groups in our activities, hopefully in the next 2 years we'll be working on that, on mapping laboratories, on mapping researchers, also attracting students, having a more aggressive, I would say, work within the meetings of the Brazilian Society for the Progress of Science and so on. So it's very good that we are raising these expectations so that for the next meeting we have more contributions from the community. And then as we move along, these possibilities and new collaborations will be coming. So thank you very much. And I would like to ask you all to be here so that we start the session at 1:30. I'm going to open the Zoom 10 minutes before, so at 1:20 it's going to be open, so I can talk to our invited panelists. And then those who are members of the panel, please be here, and so that we start on time, because people are accessing through the internet. So thank you very much. For those who are interested, we have here the restaurant of the Association of the Technicians of the University, and today is the Feijoadas Day, so it's very close to here, and our students and us, we can guide you there for those who are interested. But please be back in 55 minutes. Thank you. Thank you.